Hello. Wireless sensor networks and the Internet of Things are emerging technologies with huge potential to change the way that we understand and interact with the world. Of particular interest to us is how we can support software change or evolution in these networks, particularly when they are infrastructural networks deployed in cities or in factories or in ports, which will need to meet changing requirements and deployment conditions over time within highly constrained resources. To support this, we have developed a new concept of operating system, which is fundamentally built to evolve. This OS supports whole system evolution from hardware drivers to protocols all the way up to applications using uniform model with strong integrity and strong independence between different kinds of software change. And every kind of software change, even the most fundamental ones, occur while the system stays online, meaning minimal service interruptions across software change. And to achieve this, we have built an OS which is based on a general theory and model of software composition and evolution, uniformly applied to all of software. And we believe that future sensor networks and other computational infrastructure which has any requirement to meet changing goals or changing deployment conditions will highly benefit from this new kind of approach to building system software. Okay, so first of all, I'm going to show you how this OS, which we call Lorien, works on a single sensor node. So what we have here is a sensor node connected to my PC with a cable. So, and there is a Lorien instantiation running on this node, which includes an interactive shell component. And so whenever I type commands into the terminal that you see behind me, those commands are sent over the cable to the sensor node and are processed by the shell component, and then any output is sent back to my computer for display in this terminal. So, for example, if I type the help command, then this is sent to the shell component and it prints out a list of other commands available. So these are just commands which allow me to inspect and evolve this current software running on this node. So the top three commands, add, remove, and replace, allow me to change software, and the next three allow me to inspect software. And we also have a few extra management commands. So if I use the memstat command, for example, this prints out the memory status of all the different kinds of memory that we have on this sensor node. So for example, in MCU storage, which is program memory, we have about 14K free at the moment. Okay, to illustrate this better, this is a diagram of the currently running software on this sensor node. So this is a complete operating system made of strongly separated components. So here we see things like file systems, a scheduler, a dynamic loader, a serial port driver, and of course the shell application itself. And any part of this architecture can be very cheaply evolved in any way we like at any time. So now we're going to make some changes to the software architecture. And firstly, we're going to send across a component called net commander, which allows me to talk to other nodes in the network. So to do this, first of all, I need to send across from my PC to the node the net commander component, so that I can then integrate it into running software. So this happens like this, and this will just take a few moments. So right now a component is being transferred from my PC into the external flash of this sensor node, which looks like this. And so the general principle in Lorien is that well, first of all, we have two main areas of memory on the sensor node. We have program memory, which is executable, and that contains the currently running software on the node. And we also have secondary storage, which is external flash memory, and that's much bigger than program memory. So that's 1 megabyte compared to 48K. And so we use external flash as a kind of cache of components, which we can optionally load into program memory to become part of running software whenever we want. Okay, so this just takes a few moments. So this is a 4 megahertz CPU on the sensor node, which is writing files to external flash right now. Okay, so that's done. So now I'm going to use some commands to inspect and change running software. So first of all, let's use rs, which you see here. And that tells me the currently running software in program memory on this node. And this corresponds to the picture that I just showed you. So again, here we see a loader, we see a serial port driver, a scheduler, and the shell component itself. And I can also use ls to see all the files in external flash storage. And this includes the file that I just sent across, so this netcom file at the bottom. And there are also lots of other files that I sent across earlier, which we'll use later. So what we're going to do now is add the netcommander component into the running software system. And again, we use one of these simple commands to do this. So we use add and then netcom. Netcom itself is actually what we call a configuration fragment, and we'll see an example of what this is later. So I type enter, and that immediately gets loaded into program memory, and the netcommander component is instantiated and becomes a persistent part of the system, which means that if I was to unplug this node and plug it back in, then it would still have netcommander running as it did before. Okay, so if I type enter, I can see that I'm still actually talking to the shell right now. And netcommander is actually an interactive application which takes control of user input, but clearly it's not currently working. So I can use the ds command to inspect any missing dependencies across the whole of software. And if I do this, I see that netcommander is missing a dependency on something called file prop, and that's why it's not working right now. So to satisfy this dependency, I again use the add command, but this time with the file prop component. Again, this is in external flash already. And I press enter, and again that gets loaded very fast. Okay, but I'm still talking to the shell, so again I can press ds and see what's wrong now. So what's important to see here is that even though file prop has been loaded, Lorien has not connected netcommander to it. And this is because file prop has its own dependencies which are not yet satisfied, in this case on a Mac protocol. Okay, so now I'm going to add Mac in exactly the same way, and type ds again. And again we see Mac has its own dependencies, so the final one is radio, so this is a radio driver which is needed by Mac. And if I type ds now, I can see that Lorien has automatically satisfied Mac's dependencies on the radio driver, even though it wasn't explicitly told to do so. And finally we have a random number generator needed by Mac. And again, when I add this to the system, Lorien will automatically satisfy this dependency. And furthermore, once it sees that Mac is fully connected to its dependencies, it will then see if anyone was waiting for Mac, which in this case is file prop. And once file prop is fully connected, it will see if anyone was waiting for that, which in this case is netcom. So the actual effect of me typing add random is this is netcommander. Okay, and so what we have done here is moved from the software architecture on the left to the architecture on the right. Hopefully you can see that those two architectures are in fact quite different, and we've added things as fundamental as drivers and Mac protocols here. And the important thing to take away from that is, first of all, how Lorien tracks dependencies and doesn't allow components to connect to other components which are not yet fully connected. This is part of Lorien's integrity rules to guarantee safety in the face of even the most fundamental online software change. And secondly, I could have added all these components from the radio driver to the netcommander application component. I could have added those components in any order I wanted, and the end result would have been the same. And that is part of what we call update independence in Lorien. And that's a very important property which allows different parts of software to come and go freely without being aware of the other kinds of software currently loaded. And we'll see more examples of this later. Okay, so now that we've seen how software evolution basically works on a single node, we're going to reuse the same simple ideas to change software on the other two nodes that you see here, so the nodes in the network. And to do this, we're going to use netcommander, which I'm currently interacting with. So if I type help here, then I see netcommander's own list of commands. And these basically allow me to transfer files from the external flash chip of this node to the external flash chip of these nodes using a file dissemination service. So the first thing we're going to do here is send across a blinking light application. Very simple application to show you how this works. So I use the put command to add files to the dissemination system. So first of all, I add a configuration fragment, and again we'll see an example of this later. And I also need the blinking light component. And secondly, I need the LED driver, because this does not yet exist on these nodes, but is required by the blinking light component to actually work. And finally, we add what we call an evolution script, which I'll show you an example of in just a second. Okay, so these files right now are being sent over the radio to these other nodes in the network. And while that happens, I will just quickly show you what all these kinds of files look like. So we have three major kinds of files. We have the evolution script, which is called blink.act, and this has a list of operations of what we call evolution primitives that you're still using in the shell. And this just has two, which is add blink and add LED. The evolution script also has a list of dependencies, as in files that must exist in external flash before the script is executed. The second kind of file we have is the machine code itself, or the component which implements the machine code. And I've sent across both the blinking light application and the LED driver for this. And the third kind of file we have is a configuration fragment, which you see at the bottom of the screen here. And this specifies how any component fits into the broader architecture of the system. And this is a lot of how we get the very strong update independence of Lorien. So what you see here is firstly a configuration fragment only specifies the local dependencies of the component. And secondly, the dependencies are specified on abstract role names in the system. So LED and timer. Not specific components, just abstract names. Okay, so as soon as these two components arrive, this blinking light application and the LED driver, as soon as they arrive at these sensor nodes, then you'll see the red LED start to blink. So you'll know that that's when these components have been added to the running software image of these two nodes. Okay, so this is happening already on this node, and we'll see the other node doing the same thing in just a moment. Okay, so there we have both nodes now have received these two new components and have integrated those persistently into the running software image.